Use the theorem on inverse functions to prove that f and g are inverses of one another. Sketch the graphs of f and g on the same coordinate plane. Well, this theorem on inverse functions simply means that if I do indeed have inverses, then f of g of x and g of f of x should equal x. Let's compute f of g of x and show that that gives us x. Well, f of g of x is f of 3 minus x under the radical, which has the restriction that x is less than or equal to 3 to make that possible. Simplifying by plugging the square root of 3 minus x into f gives me the opposite of the square root of 3 minus x squared plus 3, still with this restriction that x is less than or equal to 3. This is equal to the opposite of the quantity 3 minus x, because squaring the square root undoes that operation, plus 3, and simplifying by distributing the negative sign through gives me negative 3 plus x plus 3, and the negative 3 and plus 3 cancel, leaving just x. So f of g of x is indeed x on the domain of g. We also need to show that on the domain of f, g of f of x simplifies to x. So that would say g of the opposite of x squared plus 3 will eventually need to be shown to equal x for x is greater than or equal to 0. Well, simplifying by using the rule for g says that then we have the square root of 3 minus the quantity negative x squared plus 3, again for x greater than or equal to 0, and that's the square root of, simplifying under the radical, 3 plus x squared minus 3. The 3's cancel, leaving just the square root of x squared for x's that are greater than or equal to 0. For those x's, the square root of x squared is just equal to x. If you square a positive number and then take the square root, you get x back. And that shows us that we do get x when we compute g of f of x on the domain of f, and we do get x when we compute f of g of x on the domain of g, and that means that the theorem on inverse functions conditions are satisfied, and indeed f and g are inverses of one another. To sketch the graphs of f and g, we'll note that we have here a parabola that's been flipped vertically across the x-axis and then shifted up 3 units, so its vertex will be at 0, 3. It opens downward, and when f is 0, that is when the y value is 0, we see that we have to have x being what, the square root of 3. Square the square root of 3, we get 3. The opposite of that is negative 3, and add 3 to get 0. So x equals the square root of 3 is the positive root for this parabola, and the square root of 3 is about 1.7. So we must pass through this point, and the parabola opens downward. That's the graph of f. To get the graph of g, we can think about the fact that we've just shown these are inverse functions, and inverse functions are mirror images of one another across the line y equal x. And so this point 0, 3 will have a twin at 3, 0 on the graph of g. Likewise, this point square root of 3, 0 will have a twin at the point 0, square root of 3 on the graph of g, and that gives me enough to sketch the general shape. I know this is a square root function that's been flipped around, and so I already have a good sense of what the shape is. Notice that the domain of g is the set of x's less than or equal to 3, as it's supposed to be the case, and we've got a good sketch of the two graphs here. This symmetry about the line y equal x is not coincidental. That is characteristic of any pair of inverse functions.